Hello, everyone. My name is Indranil Banik, and I'll be presenting some of the results from our paper on the KBC void and Hubble tension. So Moritz will also be doing that in the second part of the talk. My part will mainly be covering introducing MOND, what the theoretical motivations are, and how it might fit into a broader cosmological context. So this is a paper is led by Moritz, and Pavel Krupp is also a co-author on this, and we're all at Bonn. Pavel is also affiliated with Prague. So just to with if we look at galaxies and how quickly they're rotating as a function of distance from their center, so what is called the rotation curve, then you get points which sort of go sort of like that. It creates a flat rotation curve. What we actually expect based on the distribution of the visible mass is something which kind of goes like that. It follows what's called a Keplerian decline. So in this rotation curve, for example, most of the mass is within this range, and beyond that we should be seeing a Keplerian decline. This is not what we observe. So there's a big discrepancy, and this discrepancy is conventionally attributed to dark matter. So in this dark matter picture, galaxies look like this. They have a visible disk. There's a halo of dark matter surrounding the galaxy, which is shown in blue here. What you have to understand, though, is that there is no direct evidence for this dark matter. Real galaxies look like this. There may be invisible matter here, but then there might not be. So I'm going to be discussing how it might work if there actually wasn't, and why that might, in fact, be a much better idea. So first of all, why do we postulate all this invisible mass anyway? The reason is that it's sort of required if you use Newtonian gravity. Visible disk, or beyond the bulk of the visible disk, is essentially just that due to a point mass. So it's just this gm over r squared. And that has to balance the centripetal acceleration required to maintain a circular orbit. So you will get a cancellation of 1 power of r, but the second power will remain there. So the v will go down with the square root of r. Now, this is not always correct. So for example, if the velocity is close to the speed of light, then we know that you get additional relativistic corrections to this, and you cannot simply apply this equation. So that's fairly well known, but it's not critical in the outskirts of galaxies because the speeds are only about 1/10 of 1% of the speed of light. So what is important there possibly is quantum mechanics, which is what I'll explain in a sec. So classically, what we do is assume space-time looks sort of like this. It's a cartoon sketch with some kind of a mass that curves space-time. That's the typical sort of understanding of how gravity works. In reality, space-time presumably looks something like this because we cannot ignore quantum mechanics. Otherwise, it wouldn't have been possible to give this talk. So there is some additional roughness. Now, this doesn't look like it matters very much in this case. Maybe if you approximate it like this, it's reasonable. But supposing you were further away from the mass and the gravity from it was much less, or suppose the mass was much less, then would you still be able to do the same trick? So in that case, it might look like this. So the overall curvature is much smaller. In this case, you can probably tell that these small scale oscillations are much more important. You can barely tell that this is curved as a whole. So what this means is that in the second panel, like this approximation is not likely to work very well. The acceleration is too small to just ignore quantum mechanics, which we know can't in any case be ignored even here, except here maybe the corrections are very small, whereas here they may be much more significant. So just to give an idea, if you imagine space-time as being some smooth thing, and let's say though that you try and look very, very closely. So what I mean, for example, is you don't just want to know like how it works to 2 or 3 decimal places, but you want to know how it works to 4 or 5 or 8 decimal places or 10 decimal places. Eventually the quantum effects are likely to matter. The reason is that you can't sort of specify exactly how much curvature space-time has. There'll be some uncertainty. So you basically get some analog to gravitational waves, so to speak. There's always some gravitational waves, but you can't say that their amplitude is exactly 0 because quantum mechanics doesn't really allow that. What this means is that empty space probably has a small, but not 0, minimum energy, like a ground state energy, which is a familiar concept from quantum mechanics. On large scales, this would cause the universe, the expansion of the universe to accelerate, eventually to accelerate exponentially, which is something that has actually been seen. Now, the observed rate of acceleration is discrepant with what you might calculate from quantum mechanics, but it is widely thought to be the same sort of principle at stake here, that the 0 point energy density of space-time is causing the dark energy effect, which is called a cosmological constant. Now, we might not be able to calculate this, but we can measure it. We can use that to estimate when these quantum gravity effects should become important. And there's been some papers written about this. Mathematically, what one would do is this. So this is the energy density in the gravitational field classically. Now it's a non-quantum theory, so it's relatively easy to work out. And it can be done in Newtonian mechanics also. This equals the vacuum energy density, which is an empirically measured quantity for now, until we have a better idea how to calculate this. If the gravity has some particular value, which is very small compared to solar system values, but there is some threshold here, potentially. So what I want to show here is schematically how the energy density in some region of space-time might change with the gravitational field or its square. Now, if, hang on, yes, so if there wasn't any mass, then you would have the vacuum energy density. Or the ground state, as I was describing. The classical formula gives you a relation where the energy density is minus g squared over 8 pi g. In the real world, one has to combine these in some way. So maybe the total is something like this, or maybe you follow this and then it gradually curves down and it asymptotically becomes the classical line. So in any case, the asymptotic regimes should be correct, as in if there's nothing there, there's no gravity, then the rho vac is correct. And a very high gravity, then this white line is correct. But what happens in the intermediate regime? This is unknown. And that's the important thing to understand, that it's unknown. So just pretending we know what does happen is probably not a good idea, which means that theories like general relativity may well not work in that regime. Now, of course, this is an acceleration dependent effect. So if you're outside this regime, if the accelerations are much higher, then they should work. But if they're smaller, then they might start to fail. And as you get to even smaller accelerations, they'll fail by even more. So if we see something like discrepancy with classical expectations that becomes larger and larger as you get to accelerations which are smaller and smaller relative to this threshold, while the theory works pretty well above the threshold, then that would be a good sign that you have quantum effects affecting the results in ways that are not directly measurable. Ideas observationally using rotation curves of galaxies. As I was explaining earlier, the rotation curve of a galaxy, which is shown here, is much above the Newtonian expectation, which is this dashed line. But what I'm going to do now is look in more detail at the accelerations, the gravitational fields. So what's shown here is the observed acceleration, in other words, the v squared by r from the centripetal acceleration that is needed to hold the galaxy together, which recently has been directly measured for the Milky Way, thanks to the Gaia Early Data Release 3. And that's shown with these points. What's shown, this is the line of equality where the observed acceleration is equal to the Newtonian prediction. So the x-axis, sorry, this is the Newtonian prediction, and the x-axis is the Newtonian gravity from the baryons alone. Now, what is important about this graph is that the data points from this are in here, but so the data from 152 other galaxies, contributing 2,700 points almost. And they all follow this very tight relation, what is called the radial acceleration relation. And this is indeed quite remarkable, which I'll come on to later. But basically, it's just observational errors, as far as we can tell. It's consistent with like a single universal relation. There's a couple of other things to realize about this graph. First of all, the solar system is way over to the right. At the acceleration is at least 10 to the minus 6 meters per second, so and generally much higher. On the Earth, it's 10 to the plus 1, basically, so it's many orders of magnitude to the right. So we don't really know how gravity does behave in this regime, for sure. But I mean, there's data here, but it's no sort of direct experiments. The other thing to realize is what I was describing on the previous few slides regarding the quantum effects. So the threshold that I calculated on the previous slide falls here, which is basically where the accelerations inferred from rotation curves start to deviate from the Newtonian expectation, this line of equality. So what's not shown here is there's also more data. Well, I think they go up a bit further now and you in the central regions of ellipticals, for example, the accelerations are quite high. You do in fact get the G obs equals the Gn. And certainly we know that's true in the solar system. So it's only around this threshold, which is approximately 2 pi times A0, that you start to get a departure from classical expectations, which could just be a coincidence due to dark matter, but it seems unlikely because this figure does not involve galaxies in the way it's been calculated. So another important thing to understand is this is not just about the rotation curves, this talk especially. Before discussing the cosmology, another thing I wanted to explain is the satellite galaxy planes in the local group. So if you look at the Milky Way's satellites, there's satellites sort of above and below the disk, but they're not sort of distributed randomly. They're in a thin plane, as you can see. And the same is true for Andromeda. Most of the satellites are in a thin plane. They're also co-rotating within that plane. In the Milky Way case, we have 3D velocities from proper motions, and this has become clear. With Andromeda, with the radial velocities, the ones above are going away from us and the ones below are coming towards us. Fortunately, the plane is viewed close to edge on the sky. So this is also, there are a couple of satellites where we do have 3D velocities because we do have the proper motions and they are orbiting within the plane. That's recently become available. So these satellite planes are very important for reasons that I'll come on to in a sec. The first thing to realize, sort of beyond looking at these satellite planes, like, do we see satellite planes elsewhere? Actually, galaxies do form into sort of planar configurations in tidal tails. So because the tidal tail is like a thin sort of filament, it'll coalesce into like a string of sort of galaxies, what are called tidal dwarf galaxies, which will get you a satellite plane. So that doesn't prove it's the correct explanation, but alternatives are not very likely. And people have thought very hard about any other way than tidal dwarf galaxies. And it's very difficult to have primordial dwarfs in a thin plane. There must have been some dissipative mechanism to get them in a thin plane. So if they are tidal dwarfs, then they should only contain baryons in a standard context where galaxies in fact do have the dark matter halos that I was showing in blue earlier. This has been shown through many simulations that you can have galaxies interacting and form tidal dwarfs, but the tidal dwarfs will then not have dark matter in them. The problem with this is that without dark matter, you still have to explain the high internal velocity dispersions because these are observed. So you have to have strong self-gravity in the dwarfs. That is required somehow. Normally, of course, if you see unusually strong gravity in a galaxy, everyone thinks, well, that must be caused by dark matter, which is not, in fact, realistic here. I mean, it's realistic in one or two cases, but to explain the overall planar configuration, most of them should be dark matter free, which leads to the conclusion, perhaps not very popular, but the internal dynamics of the Milky Way and Andromeda satellite galaxies cannot be explained by Newtonian gravity. So just to explain briefly why that is. So in this picture, you're seeing a galaxy that's probably come in and left like a tidal tail. And over billions of years, it is quite likely that this would coalesce into like a sort of necklace of tidal dwarf galaxies, which should be orbiting within a plane. But this filament of gas is purely baryonic. You wouldn't get dark matter looking into a filament like that, for the same reason that the disk itself, it doesn't really contain substantial amount of dark matter. The dark matter is in a halo, not in a thin disk. So yeah, you can get tidal dwarf galaxies in a thin plane, but they would be purely baryonic. Now, this is perhaps, yes, it's a bit controversial. Maybe you don't believe that the local group satellite planes do in fact sort of disprove the Newtonian gravity idea that's sort of worked well for 400 years. But what you can do is help with observations of local group and nearby local universe satellite galaxies and try and quantify if they are phase-space correlated and what their properties are. This is possible at a new junior research group that's been set up by Dr. Marcel Pawlowski, who's led a lot of the work on the local group satellite planes. And this would be at Potsdam, which is near Berlin. There's a couple of PhD students that will be hired as part of this and postdoc. So yeah, you can apply for that if you like, and also ask Marcel for advice about that perhaps beforehand if you wish. So this brings me on to the hypothesis known as Milgromian dynamics, which basically um, tries to extend general relativity so it actually sort of works in galaxies. We've seen that Newtonian gravity doesn't really work there unless you sort of invent arbitrarily sort of tuned distributions of dark matter. It's possible to fit the data with a slight adjustment or correction to the Newtonian gravity. The basic idea um, is to use a Lagrangian. In this Lagrangian, the kinetic part is completely standard. The adjustment, the correction is to the gravitational part. So the gravitational action is non-standard for sure. So if you then extremize that to try and apply the Euler-Lagrange principle, then what you get is that the divergence of the gravitational field, normally that would just be the divergence of the Newtonian gravitational field, because obviously G equals Gn conventionally by definition. But here you have an extra, so nu is a function which takes the magnitude of the Gn as an argument in this formulation. Nu is a nonlinear function. Basically, it goes as a square root of Gn at low accelerations. Because of the nonlinearity, you get what is called this external field effect, where adding a constant acceleration to the system changes the internal dynamics of the system, which has in fact been observed recently by comparing the rotation curves of galaxies in different environments. They do in fact behave differently depending on the external field. So ones with a strong external field have like a declining rotation curve in the outskirts, whereas more isolated ones have a flat rotation curve. I can answer more questions about that at the end if people want, but this has recently been published in APJ. And it's the 8 sigma detection of the breaking of the strong equivalence principle, which is a foundational assumption of general relativity. So the A0 constant that is required here is approximately sort of 2 pi times smaller than the threshold that I calculated earlier from the quantum gravity and dark energy argument. So this is a empirical quantity derived from the rotation curves of galaxies. This, by the way, was fixed in 1991 and it's been used by the community since. So the reason this is going to work empirically, so if you apply this equation, the asymptotic limits are that at high accelerations, you recover the Newtonian gravity in order to fit like the solar system data. And in fact, rotation curves as well, which go a little bit above A0. But I think that some data sets go up to 30-ish A0. But at low accelerations, the G goes as a square root of the Gn, which requires, by the way, an extra acceleration to make this dimensionally correct. Now, the result of this, because the Gn goes as 1 over r squared, that means the gravity will go as 1 over r, which will cause the rotation curve to go flat. And that is certainly what we saw earlier in the data. But then the MOND was designed certainly MOND was designed to get flat rotation curves. What it was perhaps not designed to explain, or at least a lot of this data certainly it couldn't be designed to explain because it was published after MOND, is that because the Gn is proportional to the mass, the gravity is proportional to the square root of the mass, which means the rotation curve flatline level is proportional to the 4th root of the mass, which is something that can be tested not with one galaxy, but by comparing many different galaxies. And this is what is shown here. So on this graph, what's shown is the baryonic mass of the galaxy in solar masses against the VF, which is the rotation curve in the flat part of the rotation curve. So the flat line level of the rotation curve is plotted on the x-axis. Now, and this is the follows directly from here. So the MOND prediction then is this dashed line, this dotted line, which explains the data very well. The thing that is perhaps important about this is what would happen in Newtonian mechanics. In Newtonian mechanics, if you assume galaxies have a constant fraction of dark matter to baryons, then the halos would fall on this line. Now, so some of you have probably seen this and are thinking, well, that's not what would happen in ΛCDM. Okay, but in the standard cosmological paradigm, galaxies could then lose baryons from things like outflows from supernova feedback, which would in general reduce the baryonic mass. It wouldn't affect the dark matter so much. So mainly the galaxies would shift down. They would lose mass, but they wouldn't spin slower as a result. Not very much anyway, a little bit. So it's possible to go, certainly it's possible to go from this line, which is perhaps where the galaxies were initially, to here. Certainly possible. What is unusual, first of all, is that you would fall exactly on this line. So you go exactly from this line to the MOND prediction. And also unusual is that these dark and light blue points would end up the same. So the difference is that the dark blue points are star-dominated galaxies and the light blue points are gas-dominated. So presumably, if you had a star-dominated galaxy, it's formed more stars, it's had more supernova explosions. If it's gas-rich, then, well, that's not the case. It's had much fewer stars form and fewer supernovae. The amount of deviation is the same in both cases. So this light blue point is endeavor the same as all the dark blue points. And in fact, there is no correlation whatsoever between the baryonic Talley-Fisher relation that's shown here as obtained from gas-rich and star-rich galaxies or gas-poor galaxies. So this does not look like feedback is responsible at all. Now people can try and fine-tune it after the observations and try and explain this, but it's still extremely difficult to understand how this is possible. And why, in fact, you don't get a mess of points all in this entire band between the two. Or in fact, anything below this line would be possible in Newtonian mechanics. So a feedback, haphazard processes of feedback and random numbers of supernovae have obviously conspired to exactly match the MOND prediction. At least that's the standard thinking. In the MOND case, what is also important to understand, so I won't be covering this too much, but it is possible to build relativistic theories. So far I've discussed non-relativistic actions, but you can make a relativistic theory in which gravitational waves travel at the speed of light. So that is possible. Now, another thing I wanted to explain. So on the previous slide, I was showing only the flat level of the rotation curve. MOND can also fit the rest of the rotation curve, usually anyway, not in this case, obviously. So what happened here is astronomers were given a rotation curve and asked to fit the rotation curve using the distribution of baryons as inferred from sort of a photograph of the galaxy, sort of photometry, and whatever theoretical assumptions they use. So in this case, it's the MOND field equation. The same exercise is given to sort of people who favor the standard Newtonian gravity plus dark matter picture. So the CDM picture, if you like. And what happened here is that in the Newtonian gravity plus dark matter picture, it was possible to obtain a fairly good fit to the rotation curve. Still some slight wiggles, but basically it worked. In the MOND case, unfortunately, it was not in fact possible to fit the rotation curve. Some significant discrepancies were apparent at pretty much all radii. So obviously it's going to go through the rotation curve somewhere, but it's a very bad fit. So the important thing to understand here, though, is that this galaxy doesn't exist because the rotation curve that was used was of one galaxy and the image was of a different galaxy. So what happened is it didn't work in MOND, but it's not a major problem because the galaxy doesn't exist. More interesting is that even though the galaxy doesn't exist, it was quite possible to fit the rotation curve very well in the Newtonian gravity plus dark matter picture. The reason is that if you're adding an arbitrary amount of invisible mass, it is possible to fit almost anything. So that might be why the dark matter picture sort of works or is agreeing with the data. Now, however, there are certain cases where it doesn't work despite being able to add an arbitrary amount of invisible mass, which we'll come on to later. But yeah, the MOND is much more predictive on the galaxy scales, certainly. Now, the galaxies have sometimes been considered to work pretty well in MOND, but a problem is how does it work in cosmology? Is it even possible to build a viable cosmological MOND framework? So in this talk, we'll be discussing the new HDM model. So this is for the new function and for the possible candidate for the HDM, which is a hot dark matter. So this, the way this model works is like this. It's the overall pie chart for the universe is the same as in ΛCDM, by the way. The only difference is this slice of the pie reserved for cold dark matter is replaced by some form of collisionless matter, which is the name of the model is abbreviated as HDM. But what we really know about it is that it's collisionless, and it has to be fairly sort of fast moving, or it has to be a low mass particle. We'll come on to why that is later on. But certainly the cold is not correct in this picture. So the way we think this works is that you have 11 electron volt by c squared sterile neutrinos. The reason is at this mass, if these neutrinos were thermalized in the early universe, then they would have the same overall energy density as the cold dark matter in ΛCDM, leading to the same overall pie chart. So you would be able to reproduce the fact that the total amount of matter is 2 pi times the amount of baryonic matter, which is correct in ΛCDM. So I'm not going to explain why it's a factor of 2 pi, but certainly it is observationally. Now, one thing that's been shown is that if you have the same energy density as in ΛCDM, then you will get the same expansion history. The reason is the Friedmann equation in MOND works very similarly to ΛCDM. This was shown here, and there was another paper even earlier which showed that. There are some deviations, but these are very, very small, like 0.5% or less. So you get a standard expansion history, AFT, leading to standard Big Bang nucleosynthesis in the first few minutes of the universe's history. So standard abundances of deuterium and helium. The MOND obviously does matter here, but not at the background level. MOND applies to the perturbations. And the perturbations evolve according to MOND gravity rather than Newtonian gravity. So this approach has been tried in many previous publications. So predating the Hubble tension, importantly, which we'll come on to later. By the way, this is generally how MOND is thought to work in cosmology, that you apply to the perturbations only, and not to the background. Now, because you're doing that, what that will do is if you look at one small part of the universe, then any external gravitational field from surrounding structures will influence its internal dynamics. In principle, one can always just consider a sufficiently large box to include all the other structures as well. And then you won't need to worry about this. But sometimes it's convenient to think in terms of the external field effect. If you're considering a very small system and the external field is from very, very far away, then you might not want to expand your box size that much. Um, but how does one treat the external field effect in such cases? Well, if it's dominant, then that leads to analytic solutions, which you can read more about here. So these are pen and paper calculations. In general, obviously, one has to use numerical simulations to address such issues, but yeah, it's possible to get a good understanding on pen and paper regarding the external field effect in MOND. So just to summarize then, in this new HTM framework, because you have a standard expansion history, the angular diameter distance to the cosmic microwave background radiation is the same as in the standard cosmological model. At that time, at that time, the gravitational fields were about 20 times A0. They're much higher than A0. Partly this is due to all the hot dark matter, but it's just a consequence of the magnitude of the density fluctuations. So this, by the way, is the same in lambda CDM. In fact, the whole universe should have been much the same as in lambda CDM at that epoch, basically, which is important because it means that MOND would not have affected the dynamics. The way is, so although MOND might not affect the dynamics, the new could still affect the dynamics through free streaming effects, which would be much larger than for a cold dark matter particle weighing, for example, 1 giga-electron volt. However, as shown by the Planck collaboration in 2016, if the neutrino, if you have an extra neutrino with a mass more than 10 eV by c squared, then the particles are so massive that they have no effect on the CMB spectra, identical to that of cold dark matter. In other words, it doesn't really matter if you have 11 eV by c squared or 1 million. It doesn't make any difference. The free streaming effect is too small to detect. So because we are postulating massive 11 eV by c squared, obviously this is totally fine. This led to Angus and Diaferio in 2011 obtaining a very good fit to the CMB power spectrum. So the red is the lambda CDM and the blue is the new HTM framework. So another thing, although there can be slight differences, but you can also erase them with slight adjustments to the cosmological parameters as well, although very, very small adjustments, because we don't really expect any difference between MOND and lambda CDM here. Now, where MOND does become important is as the universe expands, basically another factor of 20, then the gravitational fields become less than A0. There's some transition threshold around redshift 50. MOND is important after that. So basically for the formation of the first galaxies around redshift 20 or 30, let's say, yeah, MOND would be important then, but not earlier. It'll be important later. And especially at very late times, it is going to be quite important. So regarding the sterile neutrinos that have been assumed in this model, these have been proposed independently of MOND. They've been proposed to explain why the ordinary neutrinos have a non-zero rest mass via the seesaw mechanism. This is a particle physics motivation. It's motivated not by so much by theory as by actual observations of ordinary neutrinos oscillating, which is detected at overwhelming significance on the ground. Sterile neutrinos have not been detected yet, but some hints have been found by especially the Mini-Boon collaboration and the liquid scintillator neutrino detector. So typically one gets plots something like this regarding the probability of different sterile neutrino masses. What the orange shows the results from the terrestrial experiments. One major problem with such analyses is that this cosmology line, which is basically motivated by the lambda CDM paradigm, this is obviously meaningless in the context of a completely different cosmological paradigm. However, it has nonetheless affected the results because the authors have decided to like truncate the graph at 10 eV by c squared. So obviously, if there had been a particle at 11 eV by c squared, then they wouldn't have been able to find it. But that's simply a lack of imagination on their part. So but in any case, the main thing is that there'll probably be other peaks as well at higher masses. And so far, there's no good reason to sort of assume that an 11 eV by c squared sterile neutrino is sort of impossible. And actually, yeah, in MOND, one can have a slightly higher mass as well, as I'll come on to in a sec. So sterile neutrinos, by the way, are proposed in the ΛCDM model as well sometimes as a candidate for the dark matter, but then the mass would be higher. I'll explain why that is in a sec. Before I do that, another thing that is sometimes taken as evidence for dark matter is the bullet cluster. So you see the X-ray peaks in red here in this Chandra image, and the weak lensing peaks are shown in blue here. This is where you can infer there must be a lot of gravity because background galaxy images are distorted and they kind of aligned tangentially around this blue region. So that's fairly clear that there is an offset. It's detected at approximately 8 sigma. Now, what does that actually tell us? So if you sort of believe in the ΛCDM, it tells you that you're correct, but then everything probably does. What does it actually tell you? First of all, because the gravity is stronger than A0, MOND effects would be relatively small. So it's difficult to just explain this using some quirk of gravity. It's not completely impossible, perhaps, but we don't really know how that would work. I mean, as a result, you have to explain the extra mass here without assuming that it's caused by MOND. So it needs to be caused by some collisionless matter, because if it was collisional like the gas, then it wouldn't have separated from the gas. So it needs to have like a smaller collision cross-section of the gas, if you like. Interestingly, you can see that the galaxies are sort of, there's lots of galaxies where this weak lensing peak is. So the weak lensing peak is associated with the galaxies, at least in the sense that they're at the same place. But as I was saying, this can't be explained in MOND. Maybe it can be explained in some other theory, but the easiest explanation is that you need additional collisionless matter of some sort. But what kind of collisionless matter do you need? Well, if you assume it's sort of fermionic, then you know the limit to the number density of the dark matter particles, or whatever the particles are. But assuming they're neutrinos, then we know the limit to the number density. Because we know how much mass there is, again, assuming general relativity, but this should be fine, even in MOND, then what that does, it sets a lower limit to the mass of the sterile neutrinos. They need to be more massive than 2 electron volts by c squared. Otherwise, even if their number density was equal to the maximum allowed Tremaine gun limit, they would not be able to create the weak lensing that we see here and here. But this is important. This is only 2 electron volts by c squared. Actually, if you think about how like other systems work as well, and don't make unnecessary assumptions about the behavior of gravity above A0, that is. Unnecessary assumptions below A0, and assume that it's perhaps Newtonian above A0, which seems fairly secure. What you learn is that current constraints basically only tell you that the dark matter particle has a mass more than 10 electron volts by c squared. And some of the strongest limits are coming from the CMB, but also from other galaxy clusters. So we don't actually know that the dark matter particle weighs like thousands of eV by c squared, or that it weighs more than a proton. Like, these are assumptions. Certainly there will be consistent with this limit, but it's not required. So 11 would also be fine, right? Now, to summarize what the new HGM framework can do then, because of the way relativistic theories of MOND would work, it's certainly quite possible to get a standard expansion rate history, which in turn is because we have a standard overall mass energy budget to the universe, which will lead to standard primordial element abundances. So explain the cosmic microwave background radiation anisotropies, the power spectrum, and the acoustic oscillations. The plasma physics would be much the same in MOND and lambda CDM.
Sorry, it's Sasha. I just wanted to check how many more slides do you have?
This is the last one for me.
Okay, very good. Thank you.
Okay. Yes, just summarizing. So the new HGM framework can also explain, because of the neutrinos, it can explain the bullet cluster, and also I haven't shown in detail here, but it can explain 30 virialized clusters, which are perhaps slightly easy to analyze in the bullet. Just applying the Jeans equation, you can check that out here. In these cases, one can apply the trimming gun limit calculation again. And what one realizes is that for 11 EV by c squared sterile neutrinos, the number density marginally reaches the trimming gun limit right at the center, which is a bit of a coincidence, and actually provides some of the relatively compelling evidence, I think, that the cluster scale problems, so to speak, for MOND are in fact caused by 11 EV by c squared sterile neutrinos. Now, these sterile neutrinos would not affect galaxies because of the trimming gun limit and the relatively smaller sort of size of galaxies and the smaller velocity dispersions. What would happen here is that even if the neutrinos around galaxies were packed at the trimming gun limit, because the mass, or if the mass is less than 100 EV by c squared, the halo of neutrinos would have a negligible mass. And you wouldn't be able to see it in the rotation curve. So in principle, in MOND, anything between 11 and 100 would work. But in practice, if the value was different to 11, then you would need the sterile neutrinos to not be fully thermalized in the early universe in order to get the relic abundance correct. Because new HGM essentially does not affect galaxies, galaxies are essentially governed by MOND. What this does is new HGM can solve various problems faced by lambda CDM on galaxy scales, not just the radial acceleration relation in the satellite planes, which I was describing earlier, though these are certainly important, especially given that there is another one around Centaurus A, and there should be another study on this soon. Though in this case, we don't have the internal velocity dispersions. There are a few other problems which I'll explain. So briefly, in this paper, they looked at the high prevalence of thin disk galaxies, which is unlikely if galaxies have huge dark matter halos, because then they would be merging quite often, and they would transform presumably into thicker disks or develop bulges. And here they looked at the issue that the bars in the centers of galaxies would be slowed down by dynamical friction with the dark matter halo, which would lead to a severe inconsistency with observations. There are these problems, and also with the satellite planes, if you're still thinking that they can be explained in lambda CDM, then you should look at this article, which rejects all viable lambda CDM explanations for the local group satellite planes. Now, what I haven't really explained so much is how this paradigm would work with large-scale structure. So this is what Moritz...
Sorry, Indranil, it's Sasha again. We are a little bit over time, so...
That was the end, though.
Yeah, okay, thank you. So are there important questions now, or Indranil, what do you think is best? Do we move on to the second talk and have discussion at the end?
I can take a few questions now if they're related to what I've described so far.
I would like to ask one question.
Yeah.
So, why do you expect the classical gravity regime at large scales to break down? You mean because the gravitational energy is smaller than the vacuum energy at this scale?
That's right.
Because, the question is that the classical gravity regime is usually expected to break down at smaller scales. So if we have a classical object, then it doesn't necessarily mean that, because these space-time fluctuations are expected to average over Planck scale regions to large scales. So at large scales, unless we introduce any modification, we should not expect any non-classical behavior.
Well, but do the fluctuations average out, or do they leave a residual 0-point energy which causes the universe to accelerate apart on large scales?
Yes, but they are expected to. But these small scale fluctuations are expected to average out.
Maybe they're expected to, but what I was saying is it doesn't seem like they do in the real world. In the real world, they seem to contribute some finite 0-point energy density, which is responsible for this dark energy effect.
I mean, average to this constant vacuum energy contribution. So there is no reason for us to expect that at large scales this constant vacuum energy would.
I think I understand what you're saying. So what you're saying is that if you, so if that you basically have the classical relation here. The vacuum just adds a constant.
Yes.
But this is an assumption. We don't know if that is actually correct. So all I was saying is that it may be that there isn't a correction from quantum effects, but that is an assumption. We don't know if that is how it works. You keep saying that it's expected not to matter. Well, maybe, but how do you know it doesn't in the real world?
Because at large scales, because you see this approximation of constant vacuum energy is expected to break down at smaller scales when we can no longer use general relativity as it is near the Planck scale. And at very large
Planck scale, there's probably some additional effects occur as well. But what I was trying to say is that you may expect it to that there are no quantum corrections to gravity in this regime, but maybe I expect that there are. What I was trying to say is that in the real world, it's possible that there are corrections in this regime. It's fine if you don't expect that, but it's possible.
Okay.
Can I ask a quick question?
Please, go ahead.
So what about large scale structures?
Well, that's what the next part of the talk will cover.
Okay, great.
So if there are no further urgent questions, maybe we move on to Moritz.
Okay. Yeah, hello everyone. My name is Moritz Haslbauer and I'm a PhD student at the University of Bonn, and in my talk I will present the results of our recent publication, which is called the KBC void and Hubble tension contradict lambda CDM on a gigaparsec scale, Milgromian dynamics as a possible solution. And I also would like to mention my collaborators, Indranil and Professor Pavel Krupa. The idea of our project was to test if the observed spatial arrangement of galaxies on a gigaparsec scale can be explained by the standard model of cosmology, which is the lambda CDM power time. And we also tested if a Milgromian dynamics model can work. The motivation for these projects comes from several surveys which found a huge local underdensity. And this huge local underdensity is evident across the entire electromagnetic spectrum. So the first evidence for such a local underdensity came in the early 90s in the optical. Then you can also see it in the radio observations and in X-ray. And here we focus on the paper by Keenan, Barker, and Covey. You can see here on the x-axis the co-moving distance and the y-axis the galaxy luminosity density. And at large distances, the galaxy luminosity density is very consistent between different stars and different regions. And so we can assume that this is just the cosmic mean density. But when you go now to lower distances, the luminosity density systematically drops, which is a suggestion for a local underdensity. And when you look at this bluish data point, here the density is about half time lower than the cosmic mean between a co-moving distance of 14,300 megaparsec. And this data point covers 90% of the sky. And this was obtained by counting galaxy in the near infrared regime. And this result is striking because the lambda CDM model predicts on these scales, on the 300 megaparsec scales, very small density fluctuations. So in order to test now if the KBC void is consistent or not consistent with the lambda CDM model, we use the Millennium XXL simulation, which is a very big lambda CDM simulation consistent with the WMAP1 measurements. And this simulation has a box size of 4.1 gigaparsec, which is about the Hubble radius. And therefore, we mimicked now the observations done by Keenan, Barker, and Covey. And we selected subhalos with a stellar mass larger than 10 to the solar mass, 10 power 10 to the solar mass. And we set up a grid where we calculated the luminosity density over spheres with an inner radius of 40 megaparsec and an outer radius of 300 megaparsec. And we did this for 1 million vantage points. So we expect on these scales a root mean square density fluctuation of 3.2%. This is what lambda CDM predicts on these scales. But to keep in mind, the observation tells us that the density fluctuation is 0.46. So now I came to the first results of what we obtained with the Millennium simulation. We can see here on the x-axis the apparent density contrast, and on the y-axis the frequency. And this is the distribution. So in blue we can see the distribution of the density contrast for the spheres with an inner radius of 40 megaparsec and an outer radius of 300 megaparsec. And this red line comes from observations with an uncertainty of 6%. So now, if there is an underdensity, then there must be also outflows from the central region of the voids, and this distorts the relation between the redshift and the distances. So, looking in the paper of Keenan, Barker, and Covey, they used a fixed distance redshift relation by assuming a constant Hubble constant of 70 kilometers per second per megaparsec. But in reality, the amount of volume corresponding to some range of redshift would be different to what they assumed. And this has now the effect of broadening the distribution slightly, because the apparent underdensity would have then a dispersion of 4.8%. Level. Now we consider here the impact of the KBC void on the local Hubble parameter, because there is currently a 5.3 sigma Hubble tension, because you measure a much larger local, a much larger value of the Hubble constant than globally. So on the on the x-axis, we can see the Hubble parameters locally scaled by the global value, and on the y-axis we have again the apparent density contrast. The green data point, you expect these values on average in a lambda CDM model, and this value comes from the Planck collaboration. But now you also have cosmic variance. And here we can see that even a 5 sigma INS density fluctuation only gives us a 25% antidensity and gives only a very small impact on the Hubble constant. Now I show the observations with the error ellipse, and from the observations as discussed in the previous slides, we get a much deeper local underdensity of a delta tilde value of 0.46, and also a much larger local Hubble constant, which is about 90% higher than from the Planck collaboration. And you can see here that even a 5 sigma limit, which you can reach in lambda CDM, is not enough to get within the 5 sigma error ellipse as defined by the observations. And this indicates now a very serious problem for the lambda CDM paradigm. And we found that when we combine the KBC void and the Hubble tension, this falsifies the lambda CDM paradigm at 7.09 sigma. The implications are now far-reaching, because this means that it's possible to get from the CMB boundary conditions at redshift 1100 to the z smaller than 0.2 boundary conditions as observed in the nearby universe. And since we consider here a very huge scale, namely a 300 megaparsec scale, this is also independent of a galaxy scale baryonic physics. And this implies then that one needs an effectively stronger gravity to grow structures faster in the universe, as observed. Okay. Now we are considering the KBC void in Milgromian dynamics. And to recap, the idea was now to test if, starting from the CMB boundary conditions, can the KBC void arise in Milgromian dynamics, and can this also solve the Hubble tension? So unfortunately, there is not a large enough cosmological MOND simulations available to study the existence of KBC-like voids, as we have done for the MXXL simulation in lambda CDM. And so we set up a semi-analytical model, which evolves the density contrast from redshift 9 up to present time. Motivated by observations of Karamzhev and Delikova in 2018, we assumed an initial Maxwell-Boltzmann underdensity profile with an amplitude consistent with the CMB. And as Indranil already mentioned, we assumed the standard expansion history because of the overall mass budget, because we go from cold dark matter to light stereo neutrinos. Following several other studies on structure formation in MOND, we applied MOND only to the density perturbations, and we assumed that the entire void is moving due to gravity from large-scale structures beyond the void, and the external field effect weakens the self-gravity within the void. And this affects also the velocity field of the void, which is then a constraint of our model. Now I come to the first results of our model in Milgromian dynamics. So we see here the growth of structure for a sphere with a radius of 300 co-moving megaparsec. So on the x-axis, we have the cosmic scale factor, and on the y-axis, the density contrast. And this plot shows the evolution of the density contrast in two different MOND models and in ΛCDM. So when we compare now the blue solid line, which refers to MOND, with the red solid line, which refers to ΛCDM, this demonstrates that the enhanced growth of structure in Milgromian gravitation leads to a much deeper voids than in Einsteinian and Newtonian gravity. At the 300 megaparsec in our Mondian, in our best fitting Mondian model, G was about 10% of A0, and we got an external field effect of 5.5 of A0. Now, because of the expansion of the universe, the EFE on the void should be stronger in the past. And therefore, we also plotted here a time-dependent external field effect, which has the same external field effect at present as our best fitting model. So, but in the past, this model has a higher external field effect. And the higher external field effect makes a system more Newtonian. And therefore, we need a stronger initial density fluctuation at redshift 9 in order to get a KBC-like void at present. So this is the reason why we have here a difference at the density contrast at redshift 9, and that we end up then with the same density contrast at redshift 0. So on this graph, I show the radial density profile of our best fitting model. This black dashed line is the observed value of the KBC void between 300 and 400 megaparsec, but corrected for redshift space distortion. And this line shows the observed density contrast between 600 and 800 megaparsec as derived from the KBC paper, and this value is also redshift space corrected. Now we can evolve our model in time, and we see here in brown the density profile when the universe was 0.7 gigayears old. Now we evolve this in time, so we come to 6 gigayears, 7.3 gigayears, and today we can match the inner density contrast of the KBC void at the 1 sigma confidence level, and also the outer part of the KBC void at the 1 sigma confidence level, as indicated with this blue thick solid line here. Now, I come maybe to one of the most interesting results of our paper, namely the local Hubble diagram. Such a large local underdensity affects now the cosmological parameters in the local universe. So parts of the universe beyond the void with more galaxies pull galaxies in the void outwards, and this changes now the motion of galaxies, making the universe appear to expand faster than it actually is. And this means that the local expansion rate is increased, and also the apparent expansion rate appears to accelerate at late times. Here we define the acceleration parameter, which is a second order effect and tells you an extra curvature of so Q0 bar of the Hubble diagram. Looking at the observations, Camarena and Mara jointly derived H0 and Q0 from supernova data at the redshift range of 0.023 up to 0.15. And interestingly, they found an acceleration parameter which is twice the standard value as predicted of the ΛCDM model, which is 0.55. And this is also suggestive for a local void. So in a recent paper by Kenworth et al. 2019, they concluded that a large local void is excluded by supernova data at the 4 to 5 sigma confidence level. However, in their analysis, they fixed Q0 bar at the ΛCDM predictions of 0.55. And therefore, they missed a high local Q0 value, and thus this analysis does not allow an extra curvature in the Hubble diagram. I also have to mention that there are hints of dipole in the Hubble diagram as pointed out by Colin et al. 2019 and Mikas et al. 2020. So now looking here at this figure where we have on the x-axis the Hubble constant, at the y-axis the acceleration parameter. The green data point comes again from the Planck collaboration. And now I overplot here the observations by Camarena and Mara. The black point is from the observations, and you can see the 1 and 2 sigma confidence error ellipse derived from the observations. And you can see here that there's a 4.4 sigma tension between the Planck results and the local observations. Now, I will overplot the results of our best fitting models. And in our best fitting model, where we assumed Milgromian dynamics, there we can explain the local Hubble constant and the local acceleration parameter at the 0.2 sigma confidence level. In order to check the robustness of our results, we have redone our analysis with different initial density profiles, namely with a Gaussian density profile and an exponential density profile, which you can see here. You cannot see a difference between these values here because the values are almost exactly the same, and therefore they are not distinguishable in this plot. But both analyses show that one can explain the local observations by Camarena and Mara within the 1 sigma limit. And therefore, the high local H0 and Q0 parameter are just a logical consequence in MOND because of the enhanced structure formations, which allows the formation of KBC-like voids. Now I come to the peculiar velocity field of the void in our best fitting model. Here I only show half of the void IMS size because observations indicate that we are very close to the center of the local void. And here, half of the IMS size would be around 270 megaparsec. And the entire void is moving because of the external field effect generated by structures beyond the void with 1,600 kilometer per second. But there is also a partial cancellation now between the void motion and the internal velocities within the void. As indicated, I have indicated here the internal velocities with these black arrows. And this allows also a region where much smaller than this 1,600, where we have total peculiar velocities much smaller than this 1,600 kilometer per second. And the local group is moving with around 630 kilometer per second with respect to the CMP. So this is a further constraint on our model. One can see that most of the void has a very high velocity, but also a reasonable fraction of the void has a peculiar velocity smaller than the 627 kilometer per second. And this is the most significant tension among all our constraints, as I will come to this later in the next slide. And this black line shows now where the total peculiar velocity is exactly 627 kilometer per second, and we expect that here is also the location then of the local group. And thus, we can conclude that the local group is not at a special position. Now, the kinematic Sunyaev-Seldovich effect is a relative subtle distortion to the CMB and is further blurred by thermal motions in the galaxy clusters. But at the moment, the observations, for example, by Hochscheid and Parker or Ding et al., they showed that these high peculiar velocities, especially towards the void edge, are consistent with the Kreis-Z effect. And this brings me now to a comparison of the data with the ΛCDM model and this new HDM model. So as we have shown at the first part of my talk, the KBC void causes a 6.04 sigma tension in the ΛCDM paradigm. And recently, by combining the results of Rees et al. In 2019 and Wong et al. 2020, the Hubble tension exceeded the 5 sigma threshold, and you get a 5.3 sigma value. Combining this gives a tension of 7.09 sigma. But I also would like to mention that there are more and more clear evidence that the Hubble parameter or Hubble constant differs by the early and late universe. So, for example, Aiola et al. 2020, they used the Atacama Cosmology telescope, and they found a Hubble constant very similar to the Planck results. And for the late universe, for example, Beske et al. 2020, their measurements of H0 using geometric distance measurements to mega maser hosting galaxies, which are located at 50 to 130 megaparsec, also give a very high local value of around 74 kilometer per second megaparsec, which is very consistent with the results, for example, of Camarena and Mara. Now we compare this to the new HDM model. As we have discussed in this talk, the inner part of the KBC void causes a 1 sigma tension. The outer part is also of this kind. The H0 and Q0 from supernova data give a 0.2 sigma value, and we also constrained our models from H0, which was derived from 7 strong lens time delays. And this I have not discussed in this talk, but this gave a 2.0.5 sigma. And as we have seen in the previous slide, the motion of the local group with respect to CMB gave us the highest tension, but this was still a 2.34 sigma value. And now we have three free parameters, namely the initial void size and strength of the profile and the external field effect. And taking into account that we have these 12 data points, this gives us finally a combined tension of 2.53 sigma. Now, I would like to give briefly an outlook to the stellar-wide binary test. So one possibility to test the MOND and therewith also the new HDM model would be the so-called stellar-wide binary test, and this would be complement also other cosmological tests. So stellar-wide binaries are needed with a separation of larger than 3 kilo AU. And this is, for example, like Proxima Centauri, which is the nearest star to our sun. And Proxima Centauri, for example, orbits the close binary system Alpha Cen A and Alpha Cen B at the distance of 13 kilo AU. And there, the orbital acceleration is smaller than A0, and therefore you are in the MOND regime, and this gives a boost to the orbital velocities by about 20%. So Indranil showed together with Hongxing Zhao in 2008 that one need accurate observations of about 500 weight binaries in order to distinguish Milgromian from Newtonian dynamics. And this can be done in future, for example, with the Gaia Data Relay 3 or the Thea mission. But you also have to include a statistical treatment of undetected close companions to the wide binaries. And in Newton dynamics, you would not see a difference in the velocity field for wide binaries with a separation of 3 kilo AU and wide binaries with a separation larger than 3 kilo AUs. But in MOND, you will see a difference between these two velocity distributions, regardless of a close binary perturbation. And Bitores and Sutherland used a wide binaries and showed that MOND without an external field effect is already ruled out. And also other tests, as discussed by Indranil in his part, also rules out MOND without external field effect. For example, the Shah et al. 2020 paper by looking at the rotation curves of galaxies. Now, this finally brings me to my summary and conclusion slide. So using the Millennium XXL simulation, the KBC void falsifies ΛCDM at the 6 sigma confidence level. When we combine this with the Hubble tension, which recently succeeded the 5 sigma threshold, both the KBC void and Hubble tension falsify ΛCDM at the 7 sigma confidence level. And this is far-reaching because now this tells you a failure of that the failure of ΛCDM goes now from dwarf galaxies to gigaparsec scales. And in this context, I also would like to mention the work from Elena Asensio, where also Indranil and Babel were involved as co-authors, which appeared in MNIS, and they looked at the El Gordo galaxy cluster, and they showed that this interacting system falsifies the ΛCDM at about the 6.2 sigma confidence level, which is also an indication for an enhanced structure formation. So this tells you that the meta distribution on the gigaparsec scales requires an enhanced growth of structure, and therefore we considered Milgromian dynamics because in this theory this also gives a good explanation of galactic dynamics. I can also I would also like to mention a recent paper by Indranil where he considered the disk stability of the galaxy M33. So because of this, we used the new HDM model, which is a MOND cosmology with fast collisionless matter. And in this model, the local observations can be described at the 2.53 sigma confidence level. And because of the enhanced structure formation in MOND, a KBC-like voids can form, and this simultaneously can then explain the high local H0 and acceleration parameter. So in MOND, the high local Hubble value is just a logical consequence of the enhanced structure formation. And in our paper, we also addressed common objections to a void scenario. And last but not least, I also would like to mention some blogs which describes our paper, like the DrittenStation.com and the darkmattercrisis.wordpress.com websites. And therefore, thank you very much for your attention.
Thank you, Moritz. So are there questions? Please go ahead if you have a question.
I have to see who is for.
So I have a question if, while other people are thinking. I'm confused in MOND about how you treat the horizon. So I was wondering what the relative size of the KBC void and the horizon is for all the Z values where MOND was relevant for its growth. And so I guess what I'm puzzled about is whether the void is small enough that you can calculate the external field effect from matter that is just in the horizon, or is there an issue?
Maybe Indranil can answer this question.
So at the present time, the KBC void is only extending out to about 10% at most of the Hubble distance, which I assume you mean by the horizon. So it the peculiar velocities at late times should mostly be sensitive to the structure growth at relatively later times. So for example, after the redshift 50 that we were saying is when MOND would first start to become important. So the KBC void should have been within the horizon. Regarding the effects of the external field from other structures, yes, so one certainly has to consider a larger volume than in principle. What I would say is that this issue is likely to matter in setting up accurate n-body simulations. Because we've taken a purely phenomenological approach, the external field effect that we've calculated isn't directly derived from the large-scale distribution of matter around the void, or around sort of analogs to the void in a MOND model. But yes, when doing n-body simulations, it may well be important to consider essentially this like gravity travel time effects. And at the moment, it's not entirely clear how exactly one should do that. But it would, yeah, certainly I would expect gravity from beyond the horizon to not affect the results. Yeah, so yeah, we don't know exactly how that would affect it. But these would be very, very long wavelength modes.
Thank you. Are there other questions?
I have one question. Do you see a possible connection between this MOND interpretation and the recent paper by Sarkar and Seacrest? I put the link in the chat.
No, I've seen that one. There was a YouTube talk about this one. Yes, I do actually see a strong possibility for a link there. The reason is that he explained carefully that. Okay, so maybe I can briefly summarize what they found. They were looking at quasars at redshifts of beyond 1 and searching for if they were isotropically distributed or if there was a dipole. And they've identified a dipole-like feature. And by comparing to lambda CDM, I think they found there was a 4.4 sigma sort of tension. Now, one thing that's very important to understand is that although they supposedly were looking at quasars, according to the talk they gave and I presume the article, a reasonable fraction of these quasars, so-called quasars, are actually at low redshifts because they've been selected photometrically. And that means that if you were able to enhance the amount of structure formation compared to lambda CDM, then especially at low redshifts, there would be a dipole, but that's true in lambda CDM as well, but the dipole would be enhanced. And therefore in the full sample, there would still be a dipole. Now that's also true in lambda CDM, but in lambda CDM, if you have a 4.4 sigma tension, then maybe in MOND, if you're able to enhance the structure formation and get stronger dipoles, this might fall, for example, it might be halved. And that essentially is what I think they're finding, that yes, that if you, that a large local void would be able to, if we were slightly off-center in it, or if it wasn't exactly spherical, this might well be a good way to explain the data without, by the way, giving up the as fundamental assumption of isotropy, right? Because we're not doing that.
Okay.
I have a question, if I can.
Please.
Yeah. Hi, Indranil. Thank you for the talk. Hello, Moritz. Thank you for the talk as well. So I just had a question. Since Moritz gave a comparison between lambda CDM and new HDM, even in standard model of cosmology, there are other dark matter models like HDM, tau HDM, and other models. If one were to prefer new HDM over the existing lambda CDM, what would be the theoretical motivation for one to switch for one to prefer one model over the other? Where exactly would be the key defining feature of the new hot dark matter model?
Yeah, maybe I can briefly answer that. So right, it is true that we haven't considered other models beyond the lambda CDM and the new HDM. What I would say, so much of the critical information is on this slide regarding what the new model should match. It's not theoretical so much as observational. Regarding the large scale structure, what is important is to enhance the growth of structure on sort of 300 megaparsec scales. That might happen in new HDM, maybe it happens in other theories. It doesn't happen in lambda CDM. So yeah, maybe there's other theories that could do it. However, even if you could explain this, you should also explain galaxy dynamics. So what I would say is a successful theory should explain sort of cosmology, but not forget about galaxies. It should explain things like the radial acceleration relation in galaxies and things like the Bullard cluster. So yeah, that's kind of what a successful theory would look like. In general, if a theory managed to explain like most of the observations listed on this slide, yeah, it will be worthwhile.
Is it the free streaming length scale that differs between the particles?
Well, theories can differ in many ways. Yeah, sure. One of the ways they can differ is that they can have well, they might not have dark matter, but if they do, then they might have dark matter particles of a different mass. And yes, that would change the free streaming length. So in terms of the free streaming length, then you should have a mass which is higher than 10. I think that's all that can be said reliably.
Yeah, for the free streaming length for this 11 electron volt per c squared sterile neutrinos was 3.5 co-moving megaparsec
At the
Okay.
CMB.
at the CMB epoch.
Okay. Okay, sure. Thank you.
If there are further questions or thoughts, please go ahead. Or maybe it's getting late. Moritz and Indranil, thank you very much,
Sure.
Thank you.
and have a nice evening.
You too.
Thank you. Have a nice evening.
Bye.
Bye.
Bye. Right. I'm guessing they were checking. Oh, there's only